Welcome to Ask and Learn.
Hello folks, in this video we're going to be looking at problem 44 here, which is that we have a set of propositions p1 to 3 up to n, and we want to explain why if we take, now I'll talk about what this notation actually means directly, but I'll just write this down first. I'll pause and then write it down. So we start out with these two big and signs. But we can see that we have this little I equals 1 up to n minus 1 on the first, and then j equals I plus 1 up to n. This is something that hasn't been described in the textbook yet as of the point of this chapter. But this is sort of like the and equivalent of doing the summation sigma, in that when we have this big and with I equals 1 up to n minus 1, that would be p1 plus p2, or not plus, rather, p1 and p2 and p3 all the way up to and pn minus 1. So it's just a way of doing a whole bunch of consecutive ands. So we can call that the conjunction. We have the conjunction from I equals 1 up to n minus 1, and from j equals I plus 1 up to n of not pi or not pj. Now, the first thing that I want to do here is let's take a look at a truth table for this sort of expression. So we have two propositions, P and Q, and then we'll look at the statement not P or not Q. So, like we do usually with our truth tables, we have true, 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 false, false, true, and false, false. If we have not P or not Q, then true, true, that's going to go to false. If we look at P true, Q false, then we would have not P would give us a false, but the not Q would give us a true. So that will give us a true here. Then we have not P or not Q for false and true, so again we'll have a true here, and then if both P and Q are false, we will end up with a true for not P or not Q. So we have false, true, true, true. Then, if we look at this, let's consider the statement not P and Q. Or actually, to show how we would arrive at that, at thinking about that, if we consider just the statement P and Q, then we would have true, false, false, false. So if we look at the column to the left, which was false, true, 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 we can see that the two are opposites of each other. So that would imply to us that not P or not Q is equivalent to not P and Q. So let's look at just a simple n equals 3 case. So, we have our summation. We'd have from I equals 1 up to, we had n minus 1, so it'll be I equals 1 up to 2. And then j equals I plus 1 up to 3 now we can exchange the not P or not Q for not P and Q. Well, that would give us, or sorry, it should be Pi and Pj here. That would give us the statement not P1 and P2 and not P1 and P3 and not P2 and P3. Now, if we think about what this is saying, this overall statement, if we have P1 and P2 both true, then the entire thing will have to be false, because the not of P1 and P2 will be turned to false. And then we would have one of those arguments being, or one of those components in the statement turning to false, which will turn the whole thing false since it's a conjunction. Then if we look, with the way that this conjunction is set up, the way that the indices are set up, we will be getting every possible pairing of propositions. P1, P2, P1, P3, P2, P3. Ordering doesn't matter. And then if we went up to n equals 4, again, we would end up getting every possible combination of propositions in conjunction with one another. So, in this n equals 3 case, we can see pretty directly that if a single one of these, if a single proposition is true, then none of these and statements will end up being true. If only one proposition is true, then there will be no and statement, which is true. Equivalently, if only one proposition is true, then at least, if only one proposition is true, then all of the negations of these and statements would have to be true. Think about it carefully, but that is what we arrive at here. So essentially, what we have is that our overall statement, that is the conjunction of the negation, not square root, the negation of all possible pairs. I'll say, rather, every possible pair. So, if any one of those possible pairings ends up being true, its negation would be false, turning the entire conjunction false. So, that tells us if no pairs can be simultaneously true, that tells us that there must be at most one true proposition.